Well, good afternoon. My name is Chris Barkin, and I want to welcome all of you to the William W. Hay Railroad Engineering Seminar here at the University of Illinois. Before I introduce our speakers, I'd like to take care of a few housekeeping items. The first one, as you know, please take your cell phones out, turn them on to vibrate or off so they don't go off during the presentation. If we have a fire alarm, please exit from these doors on either side of the room, take the nearest safe stairway to the first floor and exit the building. And I would ask you to carefully cross Main Street and assemble next to the Hydrosystems lab. And please use the buddy system, make note of who's on each side of you, and make sure that they have gotten out safely when we reassemble. We're not expecting any severe weather, but if we were, instead of going outside, we would go down the hallway behind me into the old part of Newmark Lab, take the first set of stairs all the way down to the basement. That's a very safe refuge. If you will be sending an attendance list around, and if you haven't already signed in or carded in, please sign that and include your name and affiliation. And if you did not receive a direct email announcement about this seminar but would like to be added to the list, then please legibly include your email address on that. We'd welcome all of those who are joining us via the internet, and we have a number of people including representatives from the Illinois Commerce Commission, URS Consulting, Patrick Engineering, North Dakota State University, TUV Rail Sciences, the University of Washington, University of Michigan Technological University, Parsons Brinckerhoff, Railstar Engineering, and U.S. Department of Transportation. We welcome all of you. We're glad you could join us today. And if you'd like to receive continuing education units for your participation, please send LB Fry an email with your information as described in the email announcement for this seminar. I'll also ask the speakers if you could, for the benefit of the internet audience, if you get a question from the audience, to try to repeat it so that they can hear it through the microphone. Do we have an announcement from the URIMA student chapter? Is our Thanks, Matt. The William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank the USDOT for their ongoing support. It is greatly appreciated by those of us here on campus as well as those participating via the internet. Railroad grade crossing safety remains one of the most important safety topics in the U.S. and indeed throughout the world. Statistical analyses have found crossing accidents to be correlated with traffic volume and certain other crossing characteristics. But a true understanding of the importance of various potential factors remains elusive. Although some crossing elements may reveal potential reasons for high accident frequency, these elements are often not included in the predictive models that are used. Better understanding of these relationships is critically important to improved allocation of resources for various grade crossing warning systems to improve safety. Professor Benekohal and his postdoctoral associate, Dr. Juan Medina, are addressing this problem through their research on novel approaches and analytical techniques to improve our understanding of the importance of various factors. Ray Benekohal is a professor of civil and environmental engineering here at the University of Illinois at Urbana-Champaign, and I'm pleased to say also a colleague of mine in transportation engineering as well as the Rail Transportation and Engineering Center. He obtained his BS, MS, and PhD degrees in civil engineering from The Ohio State University. Following completion of his studies, he worked briefly for RKA, a consulting firm in New York, before joining the faculty here at the University of Illinois in 1987. His research interests include traffic modeling, simulation, capacity analysis, transportation systems evaluation, and transportation safety, and he has published over 300 articles and reports in these fields. He's the recipient of numerous awards for his scholarship and contributions, and I'll just name a few, including the ASCE's Arthur Wellington Best Prize Paper and the Illinois ITE's Past President's Award for exceptional service to the transportation profession. He's the director of the annual Illinois Traffic Engineering and Safety Conference and is a former co-director of NextTrans, the USDOT Region 5 University Transportation Center. He is an active member of professional organizations including TRB, ASCE, and ITE. His co-presenter today is Dr. Juan Medina, who is a postdoctoral research associate here at the U of I, where he completed his PhD in civil engineering. He's been working in traffic operations for more than 8 years, and his main interests are in transportation safety, traffic signal control, ITS, and agent-based systems. He's the recipient of the ITE Illinois Section's Annual Paper Award, the Committed Student Award from the Engineering Council, and the Duluth Travel Award from the Civil Engineering Department here. He has published 16 papers in peer-reviewed journals and given more than 30 presentations. Please join me in welcoming our speakers today, Drs. Ray Benekohal and Juan Medina, who will be presenting the William W. Hay Railroad Engineering Seminar on railroad grade crossing accident analysis at the microscopic and macroscopic levels.
Yes? It's on time. Okay. Thank you, Chris. Good afternoon. I'm going to give the first part of this presentation, and Dr. Medina is going to give the second part of the presentation. So my presentation is going to be on the microscopic part, and then the modeling part is going to be given by Juan. The outline of the presentation is we briefly introduce what the issues are, and then the research questions that we faced, and then brief introduction to micro approach, the state of practice in the macro modeling, and is it possible to combine them, and the accuracy of prediction, as well as future directions. As a brief introduction, now there are plenty of railroad crossing accidents. Railroad crossing accidents are severe, costly, usually higher fatalities. And many studies in the past, as well as the recent studies, are supporting that. If you look at the graph on the left-hand side, you see that there's a positive, good trend that the number of fatalities are decreasing, but still, we are getting kind of a plateauing it toward past 4 or 5 years, around 200 or so. And Illinois trend is not as pronounced as it is the national trend, but Illinois trend is also showing some decrease. So we are going from, let's say, 30, high 20s to more like 16, 11, and so on. The sad part is that about 10% of the accidents, if we look at the past 25 years of data, about anywhere between 10 to 11% of accidents are fatal accidents. And when an accident happens at railroad crossing, it's really bad. Okay. Again, national trend is good. Illinois trend is following national trend. As you can see, the total number of accidents, as well as accident in the public crossing, is going down. But in the past 4 or 5 years, it seems that it's jumping up and down, and it has stayed at that level. That reduction, is clearly presented in this graph. It's showing, if we go from 2003 to 2007 to 2010, if you look at the number of yellow dots, for example, on the left side, on the right-hand side graph, it's more yellow dots there, but as you come closer to this left-hand side of that slide, my side, kind of, then you see that the dots are a little less, fewer dots, but still it's spread all over. So the accidents are happening all over the places, even though the numbers are reduced, but the distribution seems to be almost, all over the places. More roads, more population, more accident, as you can see, cluster in Chicago area. If we look at Illinois data and then consider this one as a sample of national data, there are close to 5,900 crossings in Illinois. Not all of them, they have accidents. About 87% of them did not have accident in the past 10 years. Please recall that. This is 10 years data. This is not 1 year data. In the past 10 years data. So roughly 13% of crossings had accidents in the past 10 years. National trend is pretty much similar. 12% of, crossings in the past 10 years, nationwide data shows that had accidents. But there are locations that they have repeated accidents. For example, in Illinois, there is one location that had 9 accidents in the past 10 years. And there's another location at 7. There are locations that had 4 accidents, 5 accidents, and 4 accidents, and so on. So this idea of, is accident completely random and we cannot do anything about it because they are going to happen, it is not necessarily true. if you look at that, there are 48 locations with 3 or more accidents. This particular location with 9 accidents, I can't say that's random. There's no randomness there. There's repeated accidents year after year. So if that's happening, can we learn something from that and do something about it? So the goal, our goal is really looking at that, looking at one accident, one grade crossing, and trying to learn from that and see whether that trend holds for the others. And if there is things like that that show a clear trend, can we take that clear trend and perhaps incorporate in our models so that our predictions are more accurate? So here's the questions. Can we spot the trend? Can we find the contributing factor? Is there something we can do, basically, that helps us to model that better, improve the models a little better, or come up with new models? And if we are going to improve and then come up with the better models, what elements do we need to incorporate? Or have we incorporated anything that we could do, and this is the end of it? We are just not going to be able to get anything better than this. So that's kind of the answers we are trying to find. But let me briefly introduce what's micro-approach. Micro-approach simply is looking at characteristics of accidents at a location and dividing it into categories and then looking at each one of them and trying to spot a trend among those categories. Simply, you can say that we are doing 3 approaches. We are taking 3 approaches to do that. Approach 1 is we sketch the intersections and put the key information on that sketch. This looks like collision diagram, but it is a little more than collision diagram. Those of you who are familiar with intersections, intersections, you have collision diagram. This is more than collision diagram. So we put the key information so you can actually visually see what's going on. In step 2, we are creating a tree structure to see whether the tree structure shows us the trend, so we can spot the trend. And in step 3, we are saying that, okay, based on step 1 and 2, is there additional information that perhaps is not in the databases but actually telling us something that look at this piece of information even though it's not in your current database? And I'm going to show you an example of that. This is that 9 accident crossing location. So we took that and then we draw a sketch of it. We draw a sketch of it, and then on the right-hand side, what you see is the sketch. On the left-hand side, the one that you see, buildings and so on, that's the view from Google Map. And then on this sketch, we put basically who is hitting who. This diagram that on the right corner, upper corner, shows who is hitting who, what speed they had, what type of collisions we had. By just looking at this diagram, this collision diagram on the right-hand side, one thing comes to your mind is like, it looks like a lot of trains are hitting cars or cars are hitting train, and then that seems to be a trend over there. At least first 5, 6 of them are showing pretty much the same thing. Okay? And then there are others, all types of accidents. So we take that approach and say, okay, it looks like based on that simple diagram, there is something actually identifiable there. Say, okay, let's look at the total number of accidents that happened there and divide that based on highway user types. They were pet accidents or all car accidents or other modes. And what was the action of the motorist there at that time? So was the person driving through the gate? Was it stopped on the gate? And so on. So these are all elements that are coded in the database. And then what was the direction of the highway user? What was the timetable direction for the train? Where was the train going? Where was the car going? So it's simple information that's available already in the database. And these, on the right-hand side of that slide, what you see, those are basically the variables that is available in the FRA database. So far, we are basically using the database. And this continues, what was the circumstance of the accidents? And then what was a little bit more about the drivers, what was the driver age and gender, and what was the weather condition. And if we group them like this, what do we spot? So we actually did that. So we took that location with 9 accidents, and one of them was the pedestrian accident. So okay, let's put that one aside. These 8 of them are all motor vehicle accidents. And then we went through that division, okay? The first level we looked at, what happened? What was the driver's motorist reaction. They throw around the gate, 4 of them. Other types, 4 of them. And then what direction was the vehicle? Vehicle was northbound. If you look at those highlighted trends, it seems that it's telling you something. Vehicle is going northbound, train is going eastbound. 4 out of 8 accidents happened there. Okay? And the other one you are looking at is vehicle going southbound, train is going eastbound. So it looks like that in this case, the train is pretty obvious. I mean, the trend is pretty obvious. It's there. All we did is just took the data and plotted this way. We are not saying that every crossing is going to have this trend. We did another one with 7 accidents, and we tried to find any trend there. No trend was shown. So in one case, it was clearly trend is there, in another one it wasn't. Then we looked at other location. This location had 7 accidents, the one that we looked, and then no matter how you divide that, there is no clear accident. There's just 1 here and 2 there, 1 there. And as a result, there is no particular trend related to the driver maneuver, the age of the driver, and things. So this is the 7 location that doesn't show the trend. We continue to say, let's look at another one, another location, a third example. In this third example, we have 5 accidents. 4 of them showing that the vehicle stopped over the gate. Well, it looks like right starting from the beginning, there's going to be a trend over there, 1 versus 4. And then we continue looking at that, and it looks like in terms of vehicle going east or vehicle going west, there is not that clear trend, even though the vehicles going west has more number than the vehicle going east. Then we looked at the train direction. It looks like there is no clear trend. There is an eastbound trend and westbound trend. It looks like as we get to the last layer of that, it seems that no, there is no obvious trend, like the example 1 that was jumping out and saying, here I am. But one thing we noticed that if you look at the age of those people involved, 4 out of those 5 accidents involved drivers older than 80. And the youngest one was only 61-year-old. So we have 5 accidents. All of them are older than 61. 4 of them are older than 80. Well, there is no further information in the database to find out why. Said, okay, now we have to look at some other information. What other information we can gather here? Why we have concentration of older driver accident at this crossing? So after looking at many possible causes, okay, then we said, why don't we look at the concentration of the senior housing units around the crossing? And here we go. That's the crossing, with the red square. And those 4 senior housing complexes are right around that crossing. Okay? So there are concentration of senior drivers around that crossing. So once you identify the problem, if you want a possible improvement countermeasure for this one, do age-appropriate, population-appropriate countermeasure. And we know from the highway world that there are a lot of countermeasures that are age-appropriate. You can do it. For example, if older drivers have vision problem, they cannot see the small print, you can put larger prints. If there is protected phase, for example, helps them rather than permitted phase, put protected phase for them. And again, we can look at the issues that they are facing at this crossing and find out what other things can be done, knowing that a lot of accidents involve older drivers. So here is a factor that was not in the database, but you can bring it in based on other information, just looking at GIS and bringing GIS into this. Now, we said, okay, let's look at the common model that predicted the accidents and see whether these common models actually are using any of those variables. Saw that, no, it doesn't. So said, well, let's look at the common model and then hopefully see if we can incorporate some of these findings that we have into the common models. For example, in the first 9 accident location, we have angle issue. Is angle included in any of these prediction models? If age is included in the prediction models and so on. And the second part of this presentation is basically going to go through this aspect that what is the current state of practice in terms of predicting of these accidents. And based on the microanalysis that we did and we have spotted certain trends, if we incorporate those in the models, can our prediction get better, or do they contribute nothing to that? So Dr. Juan Medina is going to be making the second part of the presentation and discussing about these issues, how we incorporated the micro to the macro model. We are switching, those of you who are not seeing us.
Is this okay? Sounds good? Okay, thanks. Thank you, Professor. So I'll go through the rest of the presentation, and I'll continue by describing a little bit how the USDOT model, or the current state of practice, works. This model came about from a report in 1980, and it used database that was available from 1975. This database was the result of efforts from all partners and the railroad crossings that include FHWA, FRA, AAR. And they put together this database of both inventory and the accidents that happened on each of the crossings. So this was one major effort. And since the first grade crossing handbook edition in the 80s, this model was adopted. Now, we're seeing an edition from that handbook that is from 2007, and it still uses the same model. So the most coefficients from the model remain unchanged since the 80s. The model includes the accident history for each crossing. So as you predict the number of accidents that you expect for a given location, you also kind of weight average that with the actual history from that location. And then to reflect current accident trends, since this model is from the 80s, that last value is multiplied by a normalizing constant. And we'll see that in a little more detail in the next slides. So this is the first step, and this is how the actual model looks like. So it's a multiplicative model, and it has a series of factors that it considers. Most important factor, of course, is the conflicting volume, trains and cars. And there are other factors such as the number of tracks, the number of daytime trains, if it's paved or not, the maximum speed, and so on. So it is actually very easy to use. And this same table, in this case, is shown for flashing lights or crossings using flashing lights as a warning device. Has two more categories, one more for passive warning devices, or crosswalks, let's say, and then one more for gates, or gated crossings. It's important to note that in the 80s, we didn't have four-quad gates, for example. That's one big difference that, of course, we don't see in this model. So that's the first step, finding an initial collision prediction we're calling A. And the second step is incorporating that history, past history for a specific crossing. And we're doing it this way, as is shown in number 2, and we're calling that a second prediction, that's B. That number at the end is multiplied by the normalized constant, and these are updated by FRA every few years. And it shows actually how safety has been improved over the years. If you see on the last column, or the last number to the right of the table, you see the initial normalizing coefficient from 1986. So from the moment the model was developed in the 80s using that 75 database to the first update in 86, the accidents actually reduced by 12% in the whole country, taking all nationwide crossings together. And you see in 2010, looking at the first column or the second column in the table, that now accidents are about 70% of what they were in terms of number compared to 1980 model using 1975 database. So it reflects what happens on a nationwide basis. That's the way these numbers are calculated, such that the model will predict the total number that of accidents that we see for the whole country. So that's the state of practice. That's what a lot of jurisdictions use, and that's what's actually implemented in the FRA website methodology that anyone can access. So are there other alternatives, we're asking now? Or can we just see how this model compares to more recent models that we can develop based on current databases? So we use data from Illinois as an example. So this is kind of a first step. This is not conclusive, but we wanted to see how, for a state, using considered amount of data, 10 years, how we do in terms of prediction compared to the current practice. We tried a few models, and at the end, we had the best fit for our models using a modified version of a negative binomial distribution that had extra zeros. So that's what we're calling that, what is called the zero-inflated negative binomial model. So for the testing purposes, we wanted to see the actual prediction power of the model. So 5 years of the 10 were used for model developing or model building. And the next 5 years, in this case from 2008 to 2012, were used to actually check if the predictions were good. So we're assuming we're in 2007, and we're trying to predict those 5 next years. In addition, we could have done this different, but in addition, we tried to make the comparisons more, or try to mimic what the current model did. So we divided the crossings also in the same categories: passive warning devices or crossbugs, flashing lights, and gates. This is what just to show what the model looks like. It's a regular negative binomial model, and the first term that is in parentheses show how the accidents are being reduced by a term, and that term is the probability of a crossing having 0 accidents. So in addition to the zeros that you may have from a negative binomial distribution, you have extra ones. That's kind of the whole point. Further skewing that distribution even more to have more zeros. As we saw before, accidents only happen in about 13% of the crossings. So this was very useful for model fitting. This is to give an idea what factors we found were significant for each of the 3 categories. And we're showing in this table the passive warning devices, or the crossbugs, and highlighting that the ADT and the total number of trains, so conflicting volume, were pretty much the driving factors for this type of crossing. In the next, like in this slide, we see that there's one more term that we start seeing here that is important. So when you have flashing lights, and as we saw in the examples, that it may seem that angle was actually important, that showed up clearly in the model. And what's even more interesting is that actually the lower angles are even more significant than the right angles. So crossing angle, we started seeing that is important in the model for these type of crossings. Now, this changed for when you have gates, which also makes sense. When you have gates, now the significant variable, besides the conflicting volume, was the distance to the nearest highway intersection. And that's actually, we know from our friends from the Illinois Commerce Commission, in that location that you just saw before that had 9 accidents, that was actually the problem. There's a ramp that is very close to I-90, and traffic in peak hours can back up all the way to intersection. So that's also a gated crossing. So we start seeing that there are potentially other variables that can play an important role when we're trying to predict the number of accidents. So now to the comparison. Let's, for this exercise, compare the 2 models. The current state of practice, the UIUC model, and our model that we developed with those 5 years. And we're going to do this in 2 ways. One is just by showing how the accidents were predicted by the 2 models, seeing the cumulative distribution of those. And then the other one is for ranking high accident locations, or seeing how many accidents were predicted for those that we observed had many accidents. In this slide, we're seeing the first category, the passive warning devices. And in the solid blue line in the figure, we see the actual distribution of the crashes. So as you can see, there's a very sharp increase. And that shows that accidents for those 5 years happen in just only a few of those crossings, which is expected. Now, the models show, or maybe not a very good fit to that distribution. When you see the dotted line that goes, the line that goes all the way up to about 3.5 times the number of crashes, that's the USDOT model for the passive warning devices. The model we developed, and we're testing for prediction, remember, we're not using the fitted data. That's the other dotted line that is under the solid line, and it actually predicted a similar number in magnitude compared to the crashes that we observe in the next 5 years. These are the trends for the other two groups. On the left-hand side, that should be the passive warning device, the active warning devices. Apologize for that. But we see here on the right-hand side the gates, the gated crossings. And in all three cases, even though that is not the right graph, in all three cases, the predicted model that we used was significantly better than the current model that is the USDT model. Now, this is one way to see the distribution that in which the accidents are generated. Now, another similar way, a little bit different, but it's similar, is seeing the normalized distribution of those. So how well the accidents actually fit the shape in which the crashes happen. So that's basically just by normalizing those crashes that we saw before to be 1 at the end of having 100% of the crossings. That's what we're seeing here. And we see how our model fits a little better what the actual behavior of the accidents is. And in the same way, we see for the other two categories how the dashed line, the finer dots or dashes, which is the USDOT model, they cannot imitate or mimic that sharp increase, skewing that distribution further to the left. So that's one way we can compare the models, and we kind of see in a graphic or visual way how they did. A different way is the actual ranking of those high accident locations. And that's what the states would, in practice, be using the models for. So for improving the crossings, what they normally would do is, out of the whole pot of money that you have for crossing improvements, you would have to see to which crossings you're assigning this money to, right? And that's how that's when this ranking system comes into hand or into play. So if we rank if you take the top 10 high accident locations in the predicted years, and we see how many accidents we actually predicted with our models, we see that we can do a little better than the current state of practice. That applies for all three categories. And for both, let's say if we pick top 10 locations for improvements, or if we can do improvements in top 20 locations, let's say. So in summary, we can see that improvements to the state of practice are needed, both in terms of accuracy and in identifying the contributing factors. That will lead, hopefully, to better countermeasures as well. You put in your money where you actually have those most important needs. We are using a micro approach to identify some of those variables, and in this case, we actually are seeing those variables also being reflected in the macro approach. And hopefully, the combination of those two would lead to better predictions and better rankings for better money allocation. This is an ongoing project, and this was kind of the first stage, and kind of scouting the field and see what the models would look like compared to the USDOT model. But we're doing much more, and that's part of what we're listing here as current and ongoing research. That includes different model forms and optimizing that tree that you saw in which we distributed the accidents to be dynamic. And even though it looks like a very easy way to and simple to do it manually, it gets really complicated when you start thinking about corridors and clustering crossings, where you have a branch that can incorporate, 50 accidents, and you have a combination of, 10 variables. So it's really hard at that point to start kind of discovering those trends that we easily saw for one single crossing. On the corridors, that's one of the main points that we're working on. We're not only using the FRA database, but the idea is incorporating other sources of data, demographics, socioeconomic data, population density, which we can also georeference and match with the current crossing database. This is an example of a crossing that we identified that it was important. So we start seeing how the number of accidents, and then think about the combinations that we can have. These 8 crossings, we have 25 accidents, for example. And we're not showing the results here, but there are some trends that start emerging, like the direction of the trends is very important. For example, out of these 25 accidents, about 18 happened for southbound trains, for example. The combination of micro and macro approaches can be done in different ways. One may simply add the variables, or we can also add dummy variables to include those in the macro model. We can think of different classifications, as I mentioned at the beginning, by dividing, for example, gates into the quad gates and 2-gated systems. And finally, one topic that we believe is important is how we weigh that past history into the predictions. Is it the same that in the 5 years you had 2 accidents in the first year compared to 2 accidents in the last year? That's something that we'll also analyze in the temporal way. And finally, the extension of this approach to other states, different type of regions, and try to generalize it for wider use. So that's where we are now, and we're going to continue working on this. And I think this is the end of the presentation, and we'll open for questions. Thank you.
Definitely have time for some questions. And if I could remind you to repeat the question.
Sure.
At the very end, you were talking about generalizing beyond Illinois, and Professor Benekohal started off showing Illinois trends versus national trends, and they looked like they were similar. They showed a lot of similarities. So what else does it take to kind of go towards that generalization?
Okay, thank you. The question is, what does it take to generalize what we have done for Illinois to probably a nationwide or a wider use for this same approach? And hopefully, it will be applicable on a wider basis using similar results. However, with these models, we have generated specific coefficients that we know they're optimal for Illinois, but it would be they would definitely need to be tested for other models, even though the general trend for Illinois is similar. We have a distribution for each state and also nationwide of the number of crossings with 0, 1, 2, 3, 4 accidents and so on. And they look very similar. But we don't know about the specific contributing factors everywhere. So that's something that, even though may not change a lot of the results at the end, is something we need to explore. Thanks. Any other questions?
Okay, so this question is from a slide on gated, the model of gated crossing. So you said it depends on the distance from the nearest intersection. Is that the upstream or the downstream intersection, A? And B, does it matter whether it's a minor or major intersection?
Oh, thanks. So the question is, on the gated model, when we're talking about that nearby intersection, doesn't matter if it's downstream or upstream. And what's the other part?
Does it matter if it's a major or
And it matters if it's a major or a major intersection, or a major intersection. So in terms of downstream or upstream, what we've heard from our friends from ICC, the Illinois Commerce Commission, is that it matters a lot when it's peak hours and queues back up to the crossing. So that means the intersection will be in one of the two directions. Of course, it is downstream, but we're talking about that downstream section. In terms of major or minor intersection, the database, if we want to do it automatically, it shows the nearest highway intersection. So we wouldn't have smaller intersections than that. And that could be something that we can explore using GIS, for example, since it's not going to show small streets or small signalized intersections. But that's a good point. Thanks. Any other questions? Yeah.
I have a question for Professor Benekohal. When you were talking about the grade crossing that had people with accidents who were older than 61, I noticed in your map that there was another crossing just south of there, and I was wondering if that crossing also had similar accidents. Did you look at that?
No, the question is, on that one crossing that had 5 older drivers all involved, and they were all older than 61. Next to that crossing, it seems that on that train line, there is another crossing. The question is, did we look at the adjacent crossing to see what was the pattern there? No, we didn't do that, and then one reason we didn't do that, that location did not show high number of accidents. Because when we ranked these locations by the number of accidents, that location didn't show up. But that's a good point. We should look at it and see how many accidents we had there. First of all, how many, and then the second, if there were a couple, which I doubt there were, what is their age a factor on that one? And then what's the characteristics of these two adjacent crossings? That one seems to be causing problem for older drivers, and the other one is not causing problem at all, or not causing problem to any age. We should probably look at that and see what data we have available for that. And the volume of also traffic on that, so how much traffic we have. So,
Ray, what does it take accident rate-wise to trigger the installation of some sort of protection or grade crossing?
I really don't know, but there's a criteria for going from crosswalk to flashing and flashing to gate. And I think there's a procedure for going through it, but I actually don't know exact numbers, what they are.
I have a question for Ray. In one of your early slides, you showed that distribution of the number of crossings and the number of incidents you had at each of those crossings. And the null hypothesis could be that it's random, and I would think it would conform to a Poisson distribution. Did you test that hypothesis?
You probably heard the questions, right? No, we did not actually test that. When you plot the distribution, it clearly looks Poisson distribution, and you have a very tall bar showing 0 accidents, and very quickly it drops to 1 accident, and drastically drops to 2 and 3. So it's no doubt that's going to look a Poisson distribution if we test that. Okay, but our idea was that even though the shape of the graph may look like a Poisson distribution, but what is real is that there are repeated accidents at a certain number of crossings, and that should show a trend. Assume that the occurrence of the accident is a Poisson distribution, but 9 accidents happening at one location cannot be statistical event. It's a real event. So for that reason, we wanted to see what's causing it, regardless of what shape those distributions are. And is there a trend in that 9 locations that can point out to something? And in this case, it did to the angle.
A little bit on that. We actually did for the macro, tried Poisson and negative binomial before going to the zero-inflated version. And we couldn't replicate or get even close to the variance when it comes to the Poisson or even the negative binomial. That's why we added that 0 inflation term. So for the macro models, we actually did look at the Poisson and the negative binomial.
And you're saying it did?
It did. It did fit relatively well, but the zero-inflated fit better. That's why we went with that one.
Do we have time?
Oh, yeah.
Do we have time?
Did you find there to be a greater likelihood of an accident occurring if there was an intersection within a very close proximity to the grade crossing?
Yes, if you looked at the coefficient when Juan was showing the variables and then their significance, if it is beyond 200 feet, actually it's not that relevant anymore. And it should be within that 200 feet. Was that 200, right?
200.
Yeah, within that 200 feet, then it becomes relevant. And it's the closer it is, the worse the situation gets. You know, when you have 80 feet, that's worse than when you have 120 feet, space between the two. Okay? And I think in Illinois, there is a certain distance that if the distances are below that, then you have to actually coordinate your signals. You have to have interconnected signals. So the railroad signals and the highway signal, highway signal versus highway railroad signals, they are coordinated in a manner that the queue is clear, the cars are not trapped over the railroad tracks, and so on.
Did that crossing that had the 9 incidents in the past 10 years, did that fall within that category?
Oh, definitely. That distance there is, but you know,
It is greater than 200 feet, but it is close. It's about 300-400 feet. But the queue is actually back up all the way to there. It's getting onto I-90.
Other questions from the E4 section?
On your paper, when you try to find the relationship between the accident frequency and the exposure variable, and for the traffic lane, it appears that the number of accidents doesn't go up when you have a lot of exposure. What could you explain the possible reason why the other variable like train volume and total track is go up when the number of exposure go up?
Sure. You're talking about in the paper, we have a few figures that show the direct influence of individual factors to the frequency of accidents. And we have a few figures, one showing the ADT, another one the train volume, another one the number of lanes, and the number of tracks. So there's a very clear trend of that shows increasing accident frequency as you increase ADT, train volume. But the trend is not that clear when you go to number of lanes and number of tracks. So even though in some of the models showed that the number of lanes is still significant, there's a lot of collinearity between the two, talking about ADT and lanes and train and tracks. So once you have accounted for ADT in the model, probably the influence that the number of lanes has is not that much. And even when you see individually the variables, lanes with, or roads with 2 lanes, for example, doesn't necessarily carry a lot of ADT. So the actual risk doesn't increase that much for that case. So there's not that direct influence of the number of lanes as it is with the ADT. That's why the trend doesn't show that clearly.
Okay, thank you.
Yeah, I have a question on this is why you mentioned on the page 3 on the paper that the percentage of tracks posted the mile speed limit and the train detection. Those are the you pointed out that they were missing in the state of Illinois, and they may lead to inaccurate values. So, what was the assumption to it, that to give accurate values in relation to these missing parameters?
Thanks. The FRA database is quite big, and while there is a mandate from the railroads to submit within a certain time frame the accident reports, there's no mandate to submit every update in terms of ADT, train volume, and so on. So some of these variables that we have in the inventory, some of those could be accurate, some of those could be not that accurate. So we found that, for example, speed limit was not up to date in most cases. So that variable could be very interesting for the analysis, but we didn't have it in this case. That could be obtained, though, if we combine GIS data, for example, with the FRA database. Same with other variables that were probably very interesting, like the percentage of trucks. That seems to be a good variable, but again, it seems that it was not updated. So, so there are variables like those that we wanted to use, but we couldn't in this case. But in the future, we believe we can incorporate other sources of data and then add it to the model.
Sorry, I had a related question about your data set, because I also do work with the FRA database on grade crossings. And I was wondering, have you been using the grade crossing inventory from the FRA or using the ICC data about grade crossing parameters?
Right. For this exercise, we use the FRA database, although we also have that database from ICC, which is very detailed, and it shows something that is very important and is not in the FRA database, which is the exact date and the modifications that they had in terms of warning devices. So we know, for example, about 69 crossings were updated from gates or a standard gate system to quad gates between 2003 and 4. And there's no way we can see that in the FRA database. So for this case, if we wanted to have a fair comparison between the current model that uses that database and our model, that's why we use the FRA database. But yeah, thanks.
And then I had a, I guess, related question, which was when you cross-reference the data from the inventory into the incident database, did you look at the effective date of the inventory record? So I guess what I'm trying to ask is, did you have to throw out incidents that occurred prior to the update, or did you go back and try to find the historical record?
Definitely. We looked at that because some of the values didn't quite match, so we tried to relate to a variable. That was a good variable too, which says the latest update that the crossing has had, and some of them dated before 1980. So those crossings we didn't use. Yeah, and there's a lot of filtering. Let's say ADT that doesn't make sense or is too low. Same with train volume. So there was a lot of data cleaning before the analysis.
Hang on. So this question's in regard to one of those multi-accident crossings that you described, in particular the Nagel UP, Union Pacific Northwest line. Okay, yeah. So the question is, how did you determine the direction the train was traveling in these incidents?
That's something that was tricky, because the timetable direction, we couldn't find it clearly. But we know that the train is going either south or northbound or east or westbound, based on not on the inventory, of course, but on the details from the accident record, individual accident records. However, sometimes, let's say in this case, the train could go east-west or eastbound or westbound or north or south. So that was a little bit of kind of trying to figure that out. So in this case, it's a little bit clear, because if you're going east or west, clear way to discern which one is which, and also north-south. So in this case, it was clear, but for some cases, it wasn't that clear. So it's coming from the individual accident records.
So that's the point, that you recorded the direction the train was traveling based on the accident report.
Yeah, the form that ends in 57 from the FRA.
Because this particular participant pointed out that this is the UP line where they run long rails, so to speak, or opposite from most of the rest of North America. Okay, thanks.
When you have those grade crossings in proximity of an intersection, when you had obscured sight either by buildings or by foliage, did you find an increased accident rate?
I don't think we did because we didn't have that type of information available in the database, and we didn't go and examine the cycle of the season that accident happened. But they could play a role, in terms of blocking some signs or lights and so on, especially for during that time. But I don't think we incorporated it for the
There's a little bit of information on the visibility conditions that are recorded for each individual accident. And even though those are not included in our sorting tree right now, that could be a good point. For example, adding on top of the, let's say, driver characteristics and the visibility, that what specifics from the narrative from each accident we can extract. For each accident record, there's a narrative that describes how the accident happened. So some information can be also taken from there.
If there aren't any more questions, then I'll suggest another round of applause. Thank you very much.